press the bell icon on the YouTube app and never miss another update.
Magnets. We all know that the opposite poles of magnets attract each other and the similar poles they repel. This happens due to their magnetic fields. We also know that different astronomical objects like Earth or Sun, they have their own magnetic fields. But do you ever wonder how much complicated phenomena these magnetic fields can create in our universe? So today we have with us Dr. Pallavi Bhat from Massachusetts Institute of Technology, and her current research interest is astronomical magnetic fields. Hi Pallavi.
Thank you, Shantanu.
Hi, so one serious question and don't lie, okay? So you had done so many good research works and you are in so many good research institutes. So had you ever thought that one day you will get a chance to come in Fandoo Scientists?
Oh, yes, wow. I had never thought so. Such an honor, Shantanu.
Yeah, it happens. Sometimes people don't realize many things and suddenly they find that they are in Fandoo Scientists. So how do you come into astrophysics? And you had done BTech, correct?
Yes, that's right. I did bachelor's in engineering previously instead of science, as that was considered to be more prestigious and useful, so to speak, in the way of having a good career. However, I felt pretty disconnected. The whole engineering stint to me felt pretty algorithmic.
Okay, so then you switched over to astrophysics. So did you do a PhD after your BTech?
Not really that way. I worked at a company called Montalvo Systems for a couple of years after my engineering. Um, they were building a microprocessor competing against Intel in the mobile low power PC segment. Um, the atmosphere there was pretty charged up and electric, but I didn't see myself from then doing the same thing for next 10 years.
Yeah, so what happened next? One day one apple fell on your head and suddenly you got enlightened and you thought that the entire purpose of your life is just to do astrophysics. So you left your job and started doing astrophysics.
It wasn't exactly Newtonian like that. It was more Galilean, along the lines of looking into a telescope and having an aha moment. Then I thought it would be pretty great to study astrophysics. Um, it all started with an internship at NCRA, National Center for Radio Astrophysics, back in Pune in India. There I got my first exposure to studying MSc level courses like quantum mechanics, statistical mechanics, electrodynamics, etc. All of which I found very convincing and exciting. Um, and then I eventually wrote competitive exams and got to my PhD.
So then you did a postdoc in Princeton and presently you are in MIT. So what are you currently working on?
Yes, I'm currently working on astrophysical magnetic fields, in particular a phenomenon called magnetic reconnection. Uh, this occurs when field lines come together, temporarily disconnect, and then reconnect. This can release a lot of energy. Um, the solar physicists think that this is the reason behind solar storms and flares, etc. The sun has really strong magnetic field lines, which in X-ray images can be traced to be seen like these loops sticking out of from the surface of the sun. And these field lines tend to move along with the plasma as it moves on the surface of the sun. Then these movements tend to tangle these field lines, and this tangling of the field lines can cause pinching, and thus reconnection can occur. And the reconnected field then takes the plasma along with it and leaves the surface of the sun in form of a flare. So magnetic reconnection basically can be a highly energetic event.
Yeah, but how do you know that these things are happening? Means, is there any observational proof of these magnetic reconnections?
Oh well, there are plenty of observations of solar flares. There are multiple telescopes out in space observing the sun. One of the challenges is to be able to predict these events because they cause solar storms. The plasma then travels towards the Earth, causing satellite communication disruptions. Well, also these observations hold information to the nature of the underlying event, including the timescales. One of the very long issues that have been there in the theoretical modeling of magnetic reconnection is to explain why these events occur on fast time scales, a few hours. As of now, this problem is considered to be more or less solved.
If the problem is solved, then what are you working on?
Well, the current models of reconnection are far from being a complete description. Timescale is one such constraint, but there are several other theoretical issues. A vast number of these reconnection models are highly laminar and do not incorporate turbulence. For example, the solar surface, the solar plasma is highly chaotic. So indeed, one of the challenges is to incorporate turbulence into these models. Also, the other question is to ask how much of the energy that is released in a reconnection event goes into heating of the plasma and how much goes into accelerating particles. These questions are not only important in the context of sun alone, but also in other astrophysical systems like galaxies, etc. Our group at MIT sort of does leading interesting research in this field.
Yeah, I know MIT is a really great place. So, how is the educational environment in MIT?
Yes, the environment provided at MIT is conducive to performing good research, and a young researcher can indeed have many opportunities to gain a lot of experience and skill sets required for an extended research career.
Anyway, so let's go back to your research again. So, are these magnetic fields only important in stars or planets, or there can be large scale magnetic fields like in galaxies or some galaxy clusters, etc.?
Yeah, there are large scale fields also in galaxies. One can see these beautiful spiral galaxies with large scale fields aligned along the spiral pattern. There are large scale fields also in galaxy clusters, which are the largest bound objects in the universe.
Okay, in stars I can understand there are plasma, and due to the motion of those plasmas there can be magnetic fields. In planets there is plasma in its core, and as those planets are moving, so there can be magnetic fields. But how come there are large scale magnetic fields in galaxies or galaxy clusters?
Well, firstly, galaxies and galaxy clusters also have plasma, but not as dense as in stars. So, indeed, they host large scale magnetic fields. The origin of coherent magnetic fields is a fundamental modern astrophysical question, and the popular answer is that the magnetic fields are grown and sustained via dynamos.
Dynamos means those who use in bicycles for powering the headlight.
Yes, the same principle of induction is used to amplify seed magnetic fields in astrophysical systems. In cycle, the cycle dynamo uses mechanical energy of cycling to generate currents. In astrophysical dynamo, the kinetic energy of plasma motions is used to generate an electromotive force which then amplifies the magnetic fields in the system. But note here that the source of energy is actually coming from the turbulent motions of the plasma. The plasma needs to be chaotic in order to amplify magnetic fields on a reasonably fast time scale.
Okay, so how do you study these magnetic fields? So do you run some large scale computer simulations, etc.?
Yes, a lot of astro and plasma physicists routinely use simulations to study dynamos or magnetic reconnection to be able to answer these questions about the origin of the fields or what dynamics do the presence of these fields result in.
Okay, so one of the most interesting things what people want to know from astronomers is about this dark matter. So do you also use dark matter for your simulations?
No, dark matter is used to explain galactic rotation. We use real matter to do magnetic field calculations. Also, there are some questions about the nature and existence of dark matter.
Okay, so now I have some really serious question. So how do you become such a great astronomer? I mean, did you do something special in your childhood?
Sorry?
I mean, when we were a child, we used to mug up multiplication tables like 2 2 ja 4, 2 3 ja 6, something like that. So did you do something special? Means did you mug up those things like 2 2 ja 2 square, 2 3 ja square root of 36 or something like that? Means what did you do in your childhood that you become such a great scientist?
No, we also mugged up those in the same way.
Oh, so I thought that you had done something special. Anyway, so now I have some rapid fire questions for you. Get ready.
Yep.
So Nikola Tesla or Thomas Edison?
Nikola Tesla?
Maxwell or Faraday?
Faraday. His passion is inspirational.
Isen Bose or Meghnad Saha?
Meghnad Saha?
Princeton or MIT?
MIT.
Simulations or theory?
Both, they are complementary.
Is it? So anyway, standard gravity or Max principle?
Mark's principle, alright. For interesting possibilities like the way you pointed out.
Okay, so that's all from me.
So now, I also have some rapid fire questions for you.
Okay, sure, go ahead.
Cosmology or string theory?
I like working in cosmology. String theory I feel little bit boring, but I like working in string theory too.
Heisenberg or Niels Bohr?
Heisenberg.
Quantum mechanics or classical mechanics?
I would say classical mechanics. I don't think quantum mechanics is a complete theory. I mean, it's like changing some theory just to match the experiment based on some assumptions. And so it's not, I don't think it's a complete concrete theory.
Oh, you mean to say there are some problems with quantum mechanics? Okay, anyway, next question. ECG solution or Ashok?
ECG Sudarshan?
Painting or video making?
I like painting.
That's it from me.
So thank you, Pallavi, for joining me in the show.
Thank you for having me in the show.
Okay, so that was our interview with Pallavi, and it is now your turn to click here and subscribe to this channel. So click here, click here, click here. If you don't click here, then I am not going to go. So just click here. Okay, anyway, forget it. Magnets. You all know that the opposite poles of magnets attract each other and the similar poles they repel. This happens due to their magnetic fields. You also know that different astronomical objects like Earth or
Press the bell icon on the YouTube app and never miss another update.
Hi Pallavi.
Thank you, Shantanu.
Hi, so one serious question and don't lie, okay? So you had done so many good research works and you are in so many good research institutes. So had you ever thought that one day you will get a chance to come in Fandoo Scientist?
Oh, yes, wow. I had never thought so. Such an honor.
Sun, they have their own magnetic fields. But do you ever wonder how much complicated phenomena these magnetic fields can create in our universe? So today we have with us Dr. Pallavi Bhat from Massachusetts Institute of Technology, and her current research interest is astronomical magnetic fields.